Informatics, and it is my distinct pleasure to be the first person to officially welcome you to the Pathology Informatics 2012 conference. The conference in this room is a review of Pathology Informatics, just to make sure that you're all in the right place. I'm going to go over a few housekeeping items up front before we introduce the first speaker. Sorry. So this conference has been a part of this overall conference for a long time. It was formerly known as boot camp, which is a bit harsh, but the goal is really to introduce pathology informatics to trainees as well as to non-trainees for whom pathology informatics may not be their original specialty. The idea, hopefully, is to garner interest among those of you in the audience in pathology informatics. We take our evaluations of this conference very, very seriously. The evaluations for this particular day's worth of activities will be part of the overall conference evaluation. Please make sure that you make some notes on how we can do things better, what you liked, what you didn't like. We review those, and we have incorporated the feedback from last year's conference. There is wireless internet access for the conference. The login, as you can see, is PITT, P-I-T-T, in all capital letters. The password is gold20, as you see it up there. We have a number of travel awardees, and I'm hoping that the travel awardees will stand up for a minute so that people can kind of give you your first recognition for the day. These are trainees who are either trainees in informatics or in pathology. You guys can sit down now. Yay! They all had to apply to come to this conference, and we reimbursed their travel for being here. It's actually a very competitive program. The travel awardees, like I said before, they do need to sign in the back of the room because this is tied to your reimbursement, unless you have received special dispensation from me. We also have a research mentor matching service as part of the training and education efforts that our organization does. We did this for the first time last year. The goal is to pair a trainee with a research mentor from a different institution, specifically for those trainees who may not have a lot of exposure to pathology informatics. And we had 7 trainees volunteer for the program. We had 10 faculty volunteers, so needless to say, we had a 100% matching rate to the trainees. And the nice thing about this is that we've had 5 abstracts generated for this meeting as a result of that mentoring program. And all of those are pairs of residents at one institution and a faculty member at another institution. So the program has worked very well. A few other items. Lunch is on your own. It's from 12 to 1:30, and it is outside of the conference. And Mike is making me nervous because he's walking up here and taking photos. Great. And then after the conference is over, there is a trainee reception. Now, I do need to make it clear that the reception is not just for trainees. The reception is actually open to everyone. The goal is for trainees to be able to network with other people, specifically faculty members, to help them build connections and resources for themselves in their future careers. The schedule has been changed. There's a handout of the schedule in the back of the room. The biggest change is that because the lunch was expanded in time, I've actually cut my talk down to 20 minutes, which it's about contracts, and so I think that all of you will be very happy that that talk has been reduced in time. And then the other thing is that I'm going earlier in the day and Johnson Art is going later in the day, which worked out better for all of us so that we could sync up our refreshment breaks. I do briefly want to talk about the importance of mentors. This is Jeffrey Kant, and in pathology informatics circles, he's not terribly well known. However, he's very, very well known in the world of molecular pathology. He was my fellowship director, and he had a huge impact on my life and on my career, and probably was one of the people who encouraged me the most, ironically, in the area of pathology informatics. I hope that every one of you will be able to find a mentor like this. I mean, I've benefited from having a number of mentors over the years, but for the faculty in the room and for the trainees in the room who may one day be a mentor, keep in mind that the impact that you have on your trainees can be quite powerful, even though you may not know it. And then we have a number of great mentors who are going to be giving talks to you today. I mean, how many people would you find who would be willing to take pictures of Flat Stanley? For those of you who don't have children and aren't familiar with Flat Stanley, this is a thing that elementary school kids do where they send Flat Stanley all over the place and have pictures taken. And I think Wally's going to kill me at this point. But we have other fun people who are going to be giving talks today. This is Dr. Tuthill, who's going to be giving a talk later today. And he's in the company of 2 fabulous famous women at this conference, Barb Karnbauer and Nova Smith, without whom this conference definitely would not have been possible. And this is Jim Harrison, who's going to be talking later today. He and I were both at the University of Pittsburgh together. I was a molecular fellow at the time, and so I showed up in the informatics division on more than one occasion. I'm sure this thought crossed his mind. And the other thing is to... this is my LIS manager, Liz, on the right, and this is me. This is what we're planning to do after we have a massive go live later on this year. Never underestimate the importance of your laboratory information system manager. They will make or break your ability to get anything done. So with that, let me introduce our first speaker. Our first speaker is Dr. Wally Henricks. He is the medical director for informatics at the Cleveland Clinic. He is also a surgical pathologist. He has been in this field for quite some time and has had an impact on my own career. And I am going to turn it over to Dr. Henricks.
Let me find my talk. Okay, good morning. Thank you, Alexis. Thank you for the photo. It's okay. It could have been worse, so that's good. I would also reiterate the importance of mentors and recognize certainly Bruce Friedman is my primary mentor at the University of Michigan and throughout my career, but also Mike Bisich as part of this conference. And I want to thank the organizers for the privilege to speak and to kick off the conference. And I'll also ask your forgiveness if my voice doesn't hold up or if I take an occasional swallow of water. So today I'm going to kick this off with an overview in about 50 minutes of laboratory information systems and how they interweave with laboratory operations. Of course, it's not possible to cover every aspect of LIS in 50 minutes. This is meant as an introduction and overview, primarily for those of you who have little to no exposure in laboratory information systems, but hopefully everybody will get something out of it. I'll warn you, there are a lot of slides and a lot of words. That's by design. It would fail any good, more artistic critique of a PowerPoint, but I designed the slides this way to give you something to read when you go home if necessary, instead of just more kind of telegraphic bullet points. So I may not read every word on every slide. And with that, we will proceed. So, what I hope to do today, and I'll try to remember to keep speaking into the microphone, is define the jargon in terms related to LISs and demystify some of it. Describe the central importance of dictionaries. If nothing else, hopefully you'll walk away from this talk understanding that dictionaries are pretty central to your LIS and how your laboratory works. And as I say, identify the LIS functions, how they relate to the different phases of the workflow in the laboratory. So the LIS is the engine of the laboratory. It makes it go. A car can roll downhill without an engine. You can proceed in your lab work without the LIS, but you're not going to get very far. So fundamentally, laboratory information system is a series of programs and hardware and electronic data processing and information management functions that are necessary to run the laboratory. Doctors Elovich and Aller years ago, and probably I think the first book about laboratory information systems in 1989 stated correctly, obviously, that it's a database at its heart that establishes and maintains standard definitions, that's a word we'll come back to, and information processing procedures for the laboratory. And that's in addition, of course, to the patient information that it keeps. So we'll start with architecture. So basic building blocks. We start with the fundamentals, right? Hardware, that's what the actual physical material that run the systems, and includes not only just the boxes but the network connections as well, right? The operating system, which is essentially the central nervous system of any computer system and handles the functionality and translates the application commands into action and into meaningful work. And then, as I say, these two work together. The top two layers, as I say, it's at its core a database management system, which which runs the database, right? And it's out of the scope of this talk to really get too far into databases, but to suffice it to say, this is the computerized part of the system that runs the records and files that hold the system, and then the application software is how it works. So there are a couple of architectures that I want to go over and in contrast with kind of a hybrid. So believe it or not, this is still in use in some laboratory information systems, so this slide is not out of date yet, and I've been able to use it many years. And that is host-based LIS architecture, in which you have a single mainframe computer that controls all of the LIS functions and transactions. And it holds all of the database and all of the LIS software. All right. Now, these lines represent network connections of some sort or another. Usually in a closet or a ceiling somewhere, there's a terminal server which does that, serves sessions to terminals, which are known as dumb terminals because they only have data display and input. There's no significant processing power there. They don't really run any programs. It's a keyboard and letters and numbers on a screen. Now, you can connect to these, and if those of you who work in laboratories that have systems like this, you might notice that you connect with a PC to your LIS by double-clicking on an icon. That's called a terminal emulator, and it brings up a screen that makes your PC look like, characters and numbers in your LIS. That's called terminal emulation. Rumba, Reflections, Smart Term are examples of that. So that's more or less in contrast to the more recently developed, although still not new, client-server architecture for laboratory information systems. And as its name would suggest, clients, which are the PCs where the users sit, make requests of the more powerful computers which serve functions. There's usually one large database server that holds the main database, hence the name. And then there may or may not be other servers. These could be coalesced, and then in modern architecture, these are often virtualized into individual slots in a rack, or actually on a single server using virtual management software, which again is kind of a higher order discussion. But the point is there are other dedicated functions that servers form and handle the business logic like fax, print interfaces I've shown here. And a word that's often used is this is a distributed environment because the software functions are distributed across all clients and servers. These clients, as opposed to dumb terminals, actually run software that help the LIS function. They're part of the LIS. So there's some important distinctions that this sets up, and it's not a clean break, but these are some important principles because they relate to how your laboratory functions and how your system needs to be managed, whether the lab's doing it or not. So the mainframe is usually a character-based interface as opposed to like a Windows or a Mac or a graphical. There tends to be more limited flexibility as opposed to greater configurability with a client server where you can load things like you can on any PCs. But that comes as at a price because there tend to be greater security risks and more distributed maintenance required, as all of these devices in the field require support and someone to touch them if there's a problem or whenever it's time to do an upgrade, or if the USB port didn't get deactivated correctly and someone decides to load their music collection onto the software, which has happened. Yeah, hard to believe. Whereas you get good centralized maintenance and control. And then you could argue which way of these is better. This is one big single point of failure, but there's only one, but when it fails, it's an epic fail. And as opposed to multiple points of failure, which could lead to different and a variety of users and have to run around and fix them, but the whole system doesn't go down. So in recent years, there has been the emergence of thin client in LISs. Now, this has been around now for a little while. It's not that new anymore, but many laboratories now find it is absolutely necessary to be able to run at any scale in a laboratory. So thin client's a bit of a hybrid. You have thin clients. Now, they're called thin because the application software that runs on them does not require a lot of computing resources, okay, as opposed to a fat client or a thick client, okay? And it doesn't require a lot of computer resources to run. As I say, it connects, and most of the application logic runs on a thin client server, somewhat analogous to that terminal server in the mainframe environment. And then you connect. I didn't draw any other servers like on the previous system, but the point is this mediates connections and the application. And that thin client server and this architecture is a benefit for laboratories. And how it affects, first and foremost, it's excuse me, easier administration, okay? You get centralized applications and programs, and you can push out updates from only updating the servers, and it's easier to implement, it's easier to troubleshoot. It also provides for cross-platform, so if a computer system can only run on a PC, an IBM-compatible, Windows-compatible PC, thin client could let you run it on the Macs. There's said to be less hardware requirements and costs because you don't have to buy the latest and greatest to keep up with PC or other equipment to keep up with the processing needs. Again, it's thin software, so-called, and you don't need, you can leverage older equipment. A lot of organizations use this type of thing for remote access and from off-campus locations, and it's said to have less network traffic. So all these are great benefits. Why wouldn't we just install every LIS with thin clients? Well, there are trade-offs. This adds a layer of licensing and hardware costs that you have to manage. You also have to have some expertise in the group that supports thin client. It becomes a single point of failure. So this thin client server becomes a single point of failure for any thin clients that happen to be logged into it. Vendors vary in their effectiveness of thin client implementation. Some vendors can help you, some can't, in our experience, and so that goes to the expertise in-house question. And importantly, there may be inability to do specialized functions in a thin client environment. And this is more true, at least in our current environment, with AP-LIS, when you talk about imaging and voice recognition, but it could be true in other things. So it's a question to ask, at least, if you're thinking about it. Okay, so that's the basics of the architecture. Let's move to dictionaries. So what do dictionaries contain? Anybody can call this one out. What do dictionaries contain? Words, that's true. You don't go to a dictionary for words. What do you go to a dictionary for? Definitions. There we go. That's right. So LIS dictionaries, also known as maintenance tables, define your laboratory's information framework, okay? Defines how your lab's going to run. Standardized naming convention, standardized terminology, constrain the choices for data fields, so whenever there's a drop-down list in an LIS, somebody define those choices in a dictionary somewhere. You don't just type in words or numbers. Define the dictionaries of sort, define the content and format of reports in the LIS, and they're also used to define rules and calculations, and we'll touch on these things as we go through. They define people, places, and things. I've listed only a small number of them here, and we'll have an example, but things like test definitions, worksheets, persons, what their roles are, what their access privileges are in user groups, patient locations, laboratory locations, specimen types, etc. So let's look at a dictionary. So the most important, arguably, but I think it's true, the definition in a dictionary in a CPLIS is the test definition dictionary. All right. Doesn't mean it's the first one defined, but it's what runs it. So this is an abbreviated, mocked-up version. So you have a test name, a test code, a department of the lab, what container types, worksheets, and this is where your instrument connections are. So this, we'll talk about that in a minute. Batteries or panels that this test is part of, and then what an auto verification range is. Now, some of these in turn relate to other dictionary entries, right? So core lab, you don't want someone typing in core lab and then another time core and another time, CRLAB or something like that. So your laboratory is set up by having department dictionaries. And it's similar to true for container type. You don't want to enter purple one time, lavender another time, or some other abbreviation. Again, standardized definitions of what your tube types are. And on for the battery dictionary. It's not willy-nilly. And all of these you can see would have to be defined before you can define a test definition dictionary. And this sets up, again, how your lab works and what the terminology is going to be. An auto verification dictionary sets the rules for auto verification. We'll talk about auto val a little bit. And then These worksheets are tied to an instrument interface table for instruments that are interfaced, and there's maintenance in these tables that define the communication between those particular tests and the instruments on which they are performed. So in AP LISs, and I should have said at the beginning, I'm going to also compare and contrast the AP LISs. And many dictionary types in AP LISs overlap, and they overflow in some labs, but they overlap with CP LISs. You know, there's people, there's users, there's reports, but AP operations and data flow are quite different than the clinical lab. And for instance, specimen type or part type and special stain dictionaries don't really exist in CP LISs, and but they are analogous to test definitions. So let's look at an AP LIS dictionary. So this is a part type dictionary, meaning a part of a surgical pathology case, okay? And for this one, this is defined as a lung transplant biopsy, and it has a shorthand, and it has a description, and it has synonyms, which help you look it up if you're not sure when you're accessioning a case. And then you can have different categories of specimens, for instance, an outside consult as opposed to a routine case. And then this is a histology protocol, and then there's a fee code associated with it. Usually we want to get paid. So, and these similarly link to other dictionaries. So there is a dictionary of protocols. So we can have a regular lung biopsy, a transplant biopsy, a prostate biopsy, and I'll illustrate what a histology protocol does on the next thing. But this, for instance, is, you know, 3 levels with a blank in between. And similarly, fee codes are defined, and you know, in some of these, there's also entry names for different protocols. So fee codes are defined in the previously existing dictionary. So let's look at the histo protocol. So again, there's a histology protocol that goes to a histo protocol dictionary. This particular protocol is the transplant, and it has an H&E initial, an H&E level, a MOVAT, and a GMS stain. And then each of these, in turn, build on a stain dictionary. MOVAT stain has, and some other things, but it has what to print on the label, other lookup, and then what the fee code is. Okay, so these are oversimplified to some extent, but the idea is this is how they work together. This is the guts of your LIS. This is the work that goes into implementation. So someone complains about, well, why do we call it lung transplant BX? You know, I don't like the abbreviation for BX as well. Somebody defined it in the dictionary that way. Or even better, it's really the shorthand test codes in that definition where I had hemoglobin. Everybody kind of knows what hemoglobin, HGB. But usually in LISs, your test code characters are constrained to 7 or 8 characters, so that's where you get fun and creative definitions for mnemonics that people like to complain about. Understandably, because some of them are incomprehensible. Anyway, maintenance tables tailor the LIS to your laboratory. It's critical, and I've kind of developed this point already. It's critical to successful LIS implementation, critical to effective laboratory operations. Some dictionaries must be built in sequence. When you get the LIS out of the box, some of these may be predefined, but you really have to tailor it to your laboratory. And it requires careful attention and someone who knows what they're doing with dedicated time. This is not something that someone does in between, while the batch of electrophoresis is running in their spare time. They can, start defining the tables in that part of the laboratory. All right, interfaces. I know there's a whole talk on interfaces, and that Dr. Harrison is giving, and will do a much better job than I could, but I just want to introduce it in context here. So an interface is software and connections that translate electronic messages so otherwise incompatible systems can hopefully exchange data. And LISs live in an interface environment, and they're critical to the laboratory success. So they're right up there with definitions and dictionaries. So instrument interfaces first. There are instrument interfaces and there are foreign system interfaces, and there's overlap, especially with middleware these days. But so just some terms associated with LIS instrument interfaces. Download refers to transfer from LIS to the instrument, the orders. Upload is the results coming back from the instrument to the LIS. Unidirectional or bidirectional, pretty self-explanatory. Most unidirectionals are results back. Broadcast versus query, what that means is broadcast is when an order hits the LIS based on the rules in the LIS, the orders get downloaded to the instrument right away upon order. Query means the instrument actually queries the LIS and pulls the orders when the tube gets put on the instrument, so they're not stored on the instrument. The key is the specimen number. The LIS generated barcode specimen label that identifies that container to the LIS forms the link between the orders and information in the LIS and the orders and information or protocol on the analyzer. And I just mentioned, while we're talking about instrument interfaces, increasingly there are things like handheld phlebotomy devices and AP tissue cassette engravers, point-of-care testing devices, and other things that are also considered instrument interfaces. Okay, so speaking now just though about analyzers, okay, most vendors now have off-the-shelf so-called interfaces for most laboratory analyzers and IVD equipment. But you may buy something new and then the vendor has to write a new one and you may have to work with the vendor. This is also a revenue source, so you will be paying for it. And remember, when the lab buys a new instrument, one of the famous things that sometimes laboratory section heads or directors forget to do is, oh yeah, we needed to budget for the interface also, both sides, instrument side and LIS vendor side. Interfaces are not plug and play. Interface software has to be installed in dictionaries. There has to be testing. There has to be definition of the sequence and manner and format in which both sides expect to receive and send data, and requires rigorous testing and validation and documentation of same whenever you're doing that. So, foreign system interfaces. Your LIS is connected to many other systems. We live in a connected environment. Interfaces are the lifeblood, otherwise we'd be bottled up in the lab. The most important interface of which these days is the electronic medical record or electronic health record, which stores the patient information and also sends orders to the LIS increasingly through something called computerized provider order entry, or CPOE. There's also, importantly, an admission discharge transfer interface, which you'll hear IT types refer to as ADT. It's patient management, patient demographics, patient location in the hospital. That's why when you type in a number in your hospital, that your LIS magically recognizes that number and pulls up the patient name because somebody has, well, not somebody, because that interface, if it's doing right, is populated from some registration system, that patient's number. Web portal systems, physician office system, billing, etc. HL7, again, I'm sure Dr. Harrison will cover this, and though it needs to be put in context, it is the most important data exchange standard in healthcare. You need to at least know what it is. It defines the format of messages, okay, and there are various message types in HL7, such as lab test orders and results, known as observations, the results are, patient ADT, others. HL7 consists of messages that consist of segments comprised of fields, and I think I can promise you this is all the HL7 you'll see from me. But again, the vertical lines are the delimiters between the fields. This identifies what kind of message it is, an observation. It's the first one. This one is for creatine kinase, for instance, CK. Here's the result, here's the units, here's the reference range, here's the high flag, and here's the date and time stamp. Okay, so the idea is that. So HL7 is good. It's a standard, but it doesn't make it plug and play. Does not make interfaces, not easy. You have to still do a lot of work. One thing is institutions and vendors, for that matter, can define site-specific or system-specific extensions within the HL7 standard. And then going back to this test code, HL7 has nothing to do with what you call creatine kinase in your laboratory. Okay, laboratory sets it up, or what it's called in the receiving system or sending system in the EMR, which could even be a different code. Could be CRKS or something like that. So when you do an interface, some type of translation table is necessary to convert those test codes and the cross-reference so they can talk to each other. And that's true whether it's a test code or maybe other data that aren't homogenized between systems. So interface deployment, I think I've developed it. It requires cooperation. You have the vendors, you have the laboratory people, perhaps central IT as well, and then for order entry, maybe even some clinical groups. To help offset that, institutions often now do interface engines, which is a system that routes and translates messages across multiple disparate systems. It reduces the number, the idea is it reduces the number of individual interfaces that's required. Okay, it's widespread now in healthcare organizations and improves management. So this very sophisticated diagram is meant to show what it is. So this is point to point, right? So each of these dots represents a computer system, and if they have to all be interconnected, you have to do a point to point between all of them. Here, if you use an interface engine, also known commonly as a hub, you build an interface, the idea at least is you build an interface between each system once, and then all the rules are handled here, and you can, translations and so forth, and then if this gets swapped out, you don't have to build 3 new interfaces. This just has to be rebuilt to the hub. Okay, now we hit workflow, and we will start, we will kind of go back and forth between CP and AP, pre-analytical, analytical, and post-analytical. Excuse me. Okay, so pre-analytic phase generally includes order creation and test selection, specimen collection and labeling, and specimen receipt and tracking, all of which the LIS supports. Okay, so let's talk about CPLIS first. Electronic order entry, increasingly used and with meaningful use, will be used as a requirement anywhere there's an EHR in future years. So laboratory test orders are entered in the EMR either by a clinician or by some clinician or the physician. And so right here, the menu choices are based on definitions, but not in the EMR, but in the LIS. Vice versa, I'm sorry. The definitions are in the EMR. Those may be different than the definitions in the LIS, as I mentioned. Therefore, the translation's needed. And I didn't get into LINC, as I say, just to back up for a minute, about test code definition changes and homogenizing them. LINC, I think, will be covered this afternoon, and something had to be covered. LINC, L-O-I-N-C is a test code definition and aims to standardize test codes. It's imperfect, and I think you'll hear more about that this afternoon. Anyway, back to orders. They cross an interface to the LIS. The interface design ensures correct orders are filed in the LIS based on the test code translation. You can also have paper requisition order entry, where a paper rec comes to the lab and somebody goes into the order entry function in the LIS and types it in based on the tests that are defined in the LIS dictionary. So they look up hemoglobin and it comes up like I showed you. Okay, so for inpatients now, for specimen collection and labeling, there's typically phlebotomist sweeps. The LIS assigns a specimen based on the orders for samples that are requested for the next blood draw, places them on some type of collection list or holding area. The collection lists or labels may be printed by the phlebotomists before they go to the floor, or they may go with paper recs, or increasingly LISs have handheld devices that the phlebotomist can use at the bedside to call up orders in real time and print a label. And then regardless of how the label is generated, the phlebotomist will apply that label at the point of specimen collection. For inpatient collection labeling in which the clinician acquires a specimen, such as in stat situations or hospitals that don't have laboratory phlebotomy, clinician enters the order in the EMR or completes a paper rec. If it goes into the EMR, it probably still will print a paper requisition at the point of order entry, and usually a generic label with just the patient's name and med record number will be generated from the EMR. It is conceivable that that order could cross to the LIS, and the LIS sends it back to a printer on the unit. I know in our environment we didn't have as much success with that because it takes a little bit longer for that communication to occur, and I don't want to wait. But if you can do that, you get LIS-generated labels at the point of entry, even for clinician collects. In the outpatient, it's different, right? Because you don't have a phlebotomist going around on time draws. You have a patient showing up at some point. So for interfaced orders, those orders are pulled into the LIS when the patient shows up at the draw station, or they are downloaded 24 hours or whatever before, if it's a time draw or something like that. The point is, patient shows up, the phlebotomist looks at the orders that have crossed now to the LIS, or the phlebotomist or somebody at the drawing station enters those orders into the LIS, prints the labels from the LIS, draws the specimen, applies, and we're off. Receipt and tracking for interfaced orders. When the specimen arrives in the lab, those orders are already sitting there. So you have a specimen, the lab people go in and just wand the barcode, and that changes the status. It matches the order that's already in the LIS, and specimen's tracked as received, and then confirmation that the correct things have been ordered. For paper-only requisitions, again, the lab staff orders them in to the LIS, prints the labels at that point, and the specimen is marked as a status of received in the lab. So this statusing is an important function that the LISs play as well, and typically in interface environments, that status will go back and show the clinician that, okay, it's now in lab or pending or something like that. So they can start calling, wondering where the result is. Specimen receipt and order creation. In the API, it's a little different. Okay, the LIS assigns a unique accession number, a term we refer to as accessioning. And there can be different number wheels, typically in an LIS. And sometimes, same LIS serves different functions, or there are different sections of the laboratory, so you can have different number wheels for different types of specimens. Multiple specimens are identified under a single accession number, right? So you can have multiple biopsies in a series of GI, an upper GI endoscopy. There are typically more data on the requisition that are entered, such as clinical history or a question for the pathologist, et cetera. That gets entered into the AP-LIS. And the patient demographic information is typically pre-populated, but it might not be. There are increasingly well, I don't know about increasingly, but it is possible to do order entry from an EMR into an from an EMR into an AP-LIS. It's a little more complicated to set up. Hasn't been done as widespread, but it is emerging. All right, so in terms of order creation, there are two field types in the LIS, these are generic terms. They may be different in your LIS. There's a part type that's selected from a dictionary, right? Dictionaries have definitions. Your choices are defined: colon biopsy, stomach biopsy, etc. Okay, and then maybe even what types: biopsy, resection, polypectomy, etc. So that's what's chosen from the drop-down list at the times of order entry. Now, there has to be, though, the ability to have the part description, right? So it could be a colon polyp, but maybe they wrote on the requisition large polyp at 50 centimeters. That needs to get in the system. Also, it needs to be both. So you have the free text ability to do that. Part types, as we saw, may be linked to histology protocols. AP-LIS is now print barcode label specimens that have uniquely identifying information. And again, the specimen status is updated to something like accessioned or the like within the LIS. All right, analytic work phase. These are the steps we're going to just move along. In CP-LIS, we're talking about first about work distribution within the laboratory, okay? So first, the LIS files orders for individual components of batteries, as would be expected, right? So you could have a battery that's the comprehensive metabolic panel. Each of those orders gets filed separately within the LIS and treated separately within the LIS. The LIS generates barcode labels with a unique specimen ID, as we've talked about, and then the test orders are routed virtually to the appropriate worksheets, okay? That's a throwback term to wherever the techs used to print literally a worksheet at each bench in the laboratory. Worksheets are now virtual, although they can be printed for batch work. And those worksheets, as we saw, are signed in the test definition. So the tests performed on interface instruments have LIS worksheets interface to those instrument maintenance files that define the format and structure of that interface, okay? And I talked about the download. Well, the downloads to the instrument, as I say, can be broadcast or queried. They can also occur when the order hits the LIS or when the specimen's actually received in the lab can trigger the download to the instrument, okay? Either way. Now, that's instrument interfaces. Batch tests that are manual, things like electrophoresis, for instance, orders are routed to the worksheet, and then that shift tech comes up, pulls up the worksheet function, may even print it out, and that shows the work for that batch. And then we'll talk about how those are resulted. So now we're moving to result entry. For interface instrument, the software reads the barcode specimen number, performs the tests from the orders, and sends the results back to the LIS associated with that specimen number. And the interface specifications define, again, the data sequence and format that are expected between both systems. And we talked about the worksheets linked to the maintenance in the LIS dictionary. So for tests performed on non-interfaced analyzers or that manually are batched, the technologists pull up a result entry function, worksheet function in the LIS, type in the results, verify them, and they're on their way. At this point, also footnotes or comments that explain further about the test, such as hemolysis for a high potassium if the specimen's hemolyzed, can be entered as well. There are some important rules and additional testing that you at least have to be introduced to in CP. Those are reflex testing and auto-verification, as well as simple calculation. So the first bullet talks about simple calculation. So you can do like an anion gap calculation based on results. You can set that up in your LIS. Reflex testing, a little more complicated. That's automatic generation of a new order based on results of a previous order. Commonly, for instance, titers of anti-nuclear antibody testing that's done at a screening dilution. And if it's positive, you titer it out to see how high the antibody is. Auto-verification is important. It's a talk unto itself, but basically that's final validation or verification of and release of the results in the LIS without human intervention or human review. So you can look at, you can set up, if you recall from that test definition dictionary, we had an auto-verify range defined. So if the results fall in that range and there are no other instrument flags or things like that, the results can go back out the interface or go to the report. And the criteria are based on what definitions in your LIS. Auto verification, these are just some of the criteria. In the interest of time, I'm not going to read these, but you can set them up, excuse me, on a variety of criteria. Most commonly, it's something like the technical range of the assay. You typically wouldn't use the normal range, but it depends on the test and it depends on the lab. The idea is to find that balance between culling out the important ones but not having to review a bunch of auto-verification failures that aren't clinically relevant. I mean, for the lab to be able to be intervened in. Just a word on middleware. So middleware is generically defined, I think, as rules-based processing provided by an instrument vendor or a third party that kind of sits between the LIS and the instrument, all right? And both literally and figuratively. So it's a system through which information passes before it either goes from LIS to the instrument or the results come back. Auto-verification rules can be defined in middleware instead of within the LIS. You can also do reflex ordering in the middleware. It can also do things that are instrument-specific, like automatic dilutions or repeats or smear creation for CBCs. And there can be other aspects of instrument management, like maintenance alerts and so forth, that really are out of the scope of the LIS. This is just an example of an auto-verification table identifying these are all the different choices for ranges that you can use to define what a verify range is. Here, this one is for a CBC, so if there's any flag that comes back from the instrument, like platelet clumping or whatever the flag is on an analyzer, it'll fail auto-verification, send it to a queue, someone has to review it. Okay? All right, APLIS workflow and distribution has to do with grossing and specimen preparation. So in grossing, right, that's preparation of the specimen and submission, examination specimen, dissection, and submission of tissue in tissue cassettes. The main information outputs of the grossing phase are text entry and a gross description, designation of the tissue sections in the histology module, and the marking of gross complete. So LIS interactions in this phase can include perhaps barcode verification of the specimen. The LIS may have embedded or interface speech recognition, including with templated text to foster more rapid entry of gross descriptions and more consistency. Could be interfaced with cassette labelers, as we mentioned, or cassette engravers, and at this point where gross images would be inserted into the LIS as well. For slide preparation, which is the next stage of work distribution APLIS, the LIS directs this workflow. There are predefined protocols, like we mentioned. There are histology logs. Histology logs are kind of like the worksheets. They define the work list of cases and tell the shift or for the hour or however often they're generated, tell the histotech what to cut. And then the slide labels are based on data entered in the histology module and the protocol stain definitions. We said like the MOVAT would print on the stain. Special stains are ordered in the LIS based on how they're defined in the dictionary. So you go to the order entry function in the LIS and find your stain and mark it. They're also print on specialized logs, so you can define a histology log, but then you define an immunohistochemistry log to go to the immunohistochemistry lab. In terms of the rest of work distribution, there's something that's often known as a working draft that can now be either electronic or, in our lab, we do paper, and we think that's better because you can scribble notes on it and pass things around. But that is typically, it's a paper printout with everything on the case up until the diagnosis, including previous results. And this is important. It's an important thing to have and present to the pathologist. Those of you who have paper working drafts or whatever have seen probably that there are previous results that show up, if there's any other cases in that database. But what's important to remember is you have some control typically over what shows up on the previous. You don't have to recreate the whole previous report. You can just put in the final or the final in the comment or who the pathologist was. So it does require a little configuration as well. Okay, report generation. So the entry, the final diagnosis is the final step as opposed to a verification step in the CPLIS or auto verification. We haven't quite gotten to the point where we're doing auto verification in surgical pathology. Don't sell your microscope yet. And so the final diagnosis is facilitated by predefined templates, checklists and formats, text blobs that you can blop in and configure, things like the CAP checklist, for instance, coded text entry, speech-to-text conversion, again, can be used at this phase, has its pros and cons. And then There can be also automatic entry of the CPT and diagnosis codes based on dictionary definitions tied back to part types, right? So a PAP test will typically have the same fee code. Synoptic modules provide capability to store pathology report information as discrete data elements. So this formatting and predefined templates is still a text blob, but there are now the capability, and there is now the capability in some LISs where those templates, for instance, those CAP tumor protocols can be stored in the system as discrete data elements, which is useful for searching and other types of analysis. After the entry, the final diagnosis of status is marked final complete. Pathologists edit, review, and sign out using an electronic signature, usually, although there's nothing that says you can't manually sign the reports. It's just not going to be easy to interface that report. Post-analytic, quickly, it's basically the delivery of the results and dealing with corrections. This is in common to both. Hard copy can be printed or faxed, obviously. The faxing can be automated, and again, where does the fax number come from? It can be entered manually or can be put in through the dictionary. So if you have a recurring client, they'll get their faxes automatically. So there has to be a process for keeping that updated as well, too. For electronic reporting, that's done through interfaces to the EMR, and this is what we have been learning in recent years and will even be a greater struggle for us. And the format and display of interface reports is controlled by the receiving system, not by the laboratory. So there's a laboratory responsibility to validate what those displays look like and be mindful that there could be formatting differences. PDF and rich text formatted interfaces can help preserve formatting, but the receiving systems may not be able to accommodate it. On CP, and it's the first bullet's true for AP also, but the report must be, a corrected report must be clearly identified as such and must also include the original result. Corrected report also typically includes documentation of who was called, when, and by whom. And overlay, the corrected report in the EMR overlays the previous result, but the previous is available in the audit trail. You can't pull the rug out from the clinicians who saw the first result. It's important to know how your EMR handles these things, even though that's technically not part of the LIS. Amendments and addenda are the terms that are typically used in the AP LIS world. Amendments are that, a changed report. Addendum is additional work or commentary that's added to a previously signed out report. Report formats should be configured so that it's obvious that this is an amended or addended report with some kind of banner splash at the top. For addenda, the entire report is reprinted in EMR, the new report overlays. There are a variety of other system functionalities. Again, this is you can have a day seminar in LISs. I'll just list them here. Some of these may or may not be incorporated into an LIS. Most of these are not at this point, but they could be. And again, dictionaries, framework for information processing and workflow. So if you want to understand your LIS, go grab someone and ask them to show you some of the dictionaries. Worksheets and log define the data and specimen flow and work as it goes through the lab. The LIS is central to data management throughout the testing cycle, and there are workflow differences between CP and AP. And with that, we'll call it.
So we're going to open it up to questions, and I'm going to start off by asking Wally a question, which is, we do have a number of trainees in the room, so what would be your advice as to how somebody who is interested in learning the nuts and bolts of an LIS, what would be the best thing for them to do?
Sure, that's really important, and you may have to go bug somebody, make a pest out of yourself, which is what I did and Phil Boyer did while we were at Michigan, and find out who is primarily responsible for support of your LIS. And don't start with the people who run the hardware because they won't know about the lab. But typically it'll be one of two things. It'll be either that there's somebody in the hospital who has, in the hospital IT group, who has responsibility and is kind of liaisons with the lab. But usually there are people in the laboratory, and it may be distributed. So like the chemistry chief tech or supervisor may do the chemistry definitions, and similarly throughout other areas of the lab. So a good thing is if you're on a CP rotation is just talk to the supervisor or lab manager. In a smaller lab, talk to the administrative, or not even in a smaller lab, or you can go, there's, laboratories will have an administrative director of some sort, and find that person, ask them, you know, who takes care of the LIS around here, and then go and ask them. And the place to start, I think, again, is you can ask them, okay, if you ask them, boy, you'd like to see the dictionaries, can you show me how you define a dictionary? It's like, wow, you actually know a little bit about what you're talking about. But yeah, but that is the best way. And then there is a recently published, well, there's, for APLISs, by far and away, the textbook you want to read is published by Dr. Senard, several years ago, and ASCP recently published a more recent textbook which covers CP topics as well. So those are two printed resources. But in your own environment, yeah, just go find who runs the LIS and bug them.
Any other questions?
Great, thanks.